All righty, let's go ahead and get started. So today we will continue our discussion about calorimetry, which we started last time. What we went over in the previous lecture was the first big equation that we're going to need for thermodynamics. Well, even before that, we found one of the big characteristics which we'll be dealing with for thermodynamics, of course, is temperature. And we found that just as is true for all physical characteristics in physics, as well as engineering and all the other sciences, the units you use are important. Obviously, if someone says, asks you, how far did you travel? And you say 50, well, what the heck, 50 what? 50 meters, 50 feet, 50 inches, 50 miles? That data is meaningless if you're not told what units it is you're talking about. And when working with equations, the units you use matter. If you use incorrect units, then the final answer you get may not match what it is you think you should be getting. And this happens a lot, for instance, in first semester physics. If you're a physicist, you're using the metric system. And so distances are in meters, velocity is meters per second, and so forth. But if you're an engineer in the United States, then you don't use a metric system, you use the imperial units, because that's what we use here. And so you'd use feet per second as a velocity, feet, the distance. And what that would change, for instance, is if we're talking about a force, or let's say specifically a weight, the weight of an object is, of course, mass times gravity, where gravity is the acceleration due to gravity. Well, to a physicist, that's 9.8 meters per second squared. And so if you have the mass multiplied by 9.8, you have some number of newtons as a force. But to an engineer in the United States, they would say, no, G is actually 32 feet per second squared. And so obviously multiplying the mass by 9 instead of 32 would make a huge difference in the value of the answer you would get. Now, both weights are the same weight. It's just one is in pounds and one is in newtons. And so units are important because some of the constants we use require you to have certain units for the numbers to work out correctly. Well, in thermodynamics for temperature, of course, we found that Kelvin, the Kelvin scale is what's important. And given, for instance, you know, the temperature in Celsius, if you want to know the temperature in Kelvin, it's quite easy. You take whatever it is in Celsius and you add 273 to that number. And of course, going backwards, if you know the Kelvin temperature and you want Celsius, you just take away 273. Okay, so it's very easy to convert Kelvin and Celsius because the Kelvin system is based off of the Celsius system or the centigrade system. It's just that where Kelvin starts, its 0 point, is at a different place than where the Celsius system starts its 0 point. Celsius starts 0 at freezing water. Kelvin says water is not important to the universe. We're going to make the 0 point the coldest possible temperature. So that will be 0. And so their starting points are different. But as you increase or you change the temperature, the Kelvin and the Celsius change is the same change. The actual unit of a Kelvin versus a degree Celsius is the same change. So that's the first thing we have to understand is as we go through thermodynamics, we better be using Kelvin temperature rather than Fahrenheit or Celsius. And by the way, I didn't mention this, but just like there's Kelvin for the Celsius system, there is that same type of thing for the Fahrenheit system, and that's called R, the Rankine system. or Rankine. That's like the Kelvin version of Fahrenheit. So 0 Rankine is like absolute 0, and then everything else is like a Fahrenheit degree above it. But of course, we don't care about that. What we want is Kelvin. So every equation we're about to use that requires you to plug in a value for temperature, make sure the temperature is in Kelvin. And then I mentioned that there are special cases where if instead of asking for the actual temperature, the equation wants the change in temperature, those cases you can use Celsius if you wish, because a change in Celsius is a change in Kelvin. From there, we got our first big equation. This equation tells you how much heat is required to change the temperature of an object by a certain amount. And that equation is Q, the amount of heat energy required, is given by, first of all, C, which is called the specific heat. This is what material are you talking about? Is this a piece of wood? Is this metal? Is this styrofoam? What is this material? Because each material reacts differently to heat. Then there's M, the mass. How much of the material do you have? Obviously, if you have a heck of a lot of the material and you need to change all of its temperature, that's going to take more heat than if you only have a little bitty piece of the material and you want to change its temperature. And then, of course, delta T is how much do you want to change the temperature? You want to change it by a lot, it takes more energy. If you only want to change it by a little bit, it takes less energy. And so there's our big equation for calorimetry. And what we saw was we can ask questions like, given a piece of aluminum whose specific heat is 300, if you have half a kilogram of aluminum and you want to change the temperature by 5 degrees, how much energy is required? That's the kind of question that this particular equation can answer. Of course, what we want to do is something a little bit more interesting than that, because who cares how much energy is required? It's like, okay, well, it takes 5,000 joules of energy to do it. All right, whatever. What's more interesting are instances where you may have multiple objects all in the same system. Each object is different and it starts at different temperatures. And you say, if I put all these objects together and let them sit a while, the hotter objects will give off energy and the colder objects will take that energy in to heat up until such time as everything gets to the same equilibrium temperature. And so you could ask, what would this equilibrium temperature be? That's the kind of thing we want to get to with calorimetry. That's more interesting. But how do we do something like that? Given this is the equation we have to work with, how can we mess with multiple objects at the same time? And so what we do is we use another piece of, another concept of physics, which is the conservation of energy. The conservation of energy says, look, let's say I have some system, and in this system, I place 2 objects, object 1 and object 2. And I'm just going to assume, for the sake of assuming, that object 1 is at a higher temperature than object 2. It could be the other way around. It could be 2 is hotter than 1. Doesn't matter. The question is, what would happen? Well, what would happen is 1 having a higher temperature means it has excess energy. And excess energy means the molecules which comprise this object are vibrating pretty strongly. And that vibration gives off energy. Maybe it's bouncing and touching and hitting the other object. And in doing so, gives off some energy. Obviously, if you have one object sitting there doing nothing and an object collides, the colliding object will give some of its energy to the object that was just sitting there. And so object 1 being at a higher energy than object 2, his molecules are moving faster and will run into molecules of object 2, giving it some energy. So what you would have is some transfer of energy from the hotter object to the colder object. And this will continue to happen until such time as they're both at the same temperature. Because once they're both at the same temperature, then neither one is hotter than the other. So the energies are just equalized. They don't transfer energy anymore. So if that's the concept we have, and we know we've closed the system, so there's nothing outside of these two objects to give energy into the system, and also we're not allowing the heat to leave, it's stuck in this system, then what we have is whatever energy that object 1 gives away must go somewhere. And where does it go? It must go to object 2. It can't leave, and it can't just sit there without going somewhere. Thus, whatever object 1 gives, object 2 takes. And likewise, whatever object 2 gives, object 1 would take. And so, if that's true, then we could say that Q, the amount of energy that object 1 has or gives away, added to whatever energy object 2 gives away or takes in, must be equal to 0. They balance. And you say, well, look, I'm adding two things together. How can I get 0? Well, the first way is if they're at the same temperature, then the amount of energy 1 gives is 0, and the object 2 gives is 0. So 0 plus 0 is 0. That's fine. The other way this could happen is if one of them is a negative number and the other one is a positive number. And indeed, that's what this case is. If object 1 is hotter than object 2, object 1 will give energy and object 2 will take energy in. So if you give energy, you're losing the energy. Thus, you have a negative change. And object 2 gaining the energy would have a positive change. It's gaining that energy. So even though it looks like you're adding two things together, really one of them's a negative thing and the other one's a positive thing. So such that they add up to 0. Once we have this concept, then I know exactly what to do. I say, look, I don't know the value of Q1. I don't know exactly how much energy object 1 gives away, but I could calculate it. I could say that's Cm delta T for object 1. And then the amount of energy that object 2 will get, I don't know his number, but I do know whatever it is, it's Cm delta T for object 2. So there's my Q1 plus Q2 will be equal to 0. And now you see we have an actual equation where we could plug data into it to solve for something we may want to solve for. This is the key to solving the types of problems we're going to have here with calorimetry. Now, what exactly we're solving for will change depending on the question. Sometimes I may want to know what will be the final temperature of the system. Sometimes I may want to know how much of an object should I add such that I get this final temperature. Or if I have these two objects together and they get to this final temperature, what must have been the initial temperature of object 2? I can ask any of these questions, doesn't matter which one, and use this equation or this style of equation to solve for that thing. It's just which one of these variables is my unknown. Because what you're going to find is no matter what question you're given, you would set it up in this fashion. If there's more than two objects, then you'd have a Q1 and a Q2 and a Q3 and a Q4, however many objects there are. But you'll be given a problem where you have all the data. Every one of these variables you'll have a number for, except one. Maybe it's the mass of object 2. Maybe it's the final temperature of the system. Maybe it's the initial temperature of object 5. Whatever the one unknown is, that's your one unknown. Everything else is numbers. And so it may look like a long equation if you have multiple objects, but it's just algebra. Whole bunch of numbers, one unknown, you solve for the unknown. So that's going to be the key. That's how we're going to solve problems for calorimetry, at least this first half. Again, I mentioned towards the end of last class that there's a second half to calorimetry, which involves a little bit more complicated of a system where things can melt or boil or things like that. For now, we're going to skip that. We're just going to ignore it and only work on problems where that doesn't happen. After we're used to this, then we'll add in that complication and see how it changes what we do. It really doesn't change it much. We just add an extra term in here. But for now, there's no use in complicating it more than it needs. Let's do the simpler versions first and see the basics. So let's do an example. Let's say you have 1 kilogram of coffee at 90 degrees Celsius in an aluminum cup whose mass is 150 grams. Okay. You'd like to cool down this coffee to 70 degrees Celsius by adding milk whose initial temperature is 5 degrees Celsius. The question is, how much milk should you add? So there's our question. Now, before we do it, I need to give you a few more pieces of information. Let's see, for coffee, be 4,000. Let the specific heat for aluminum be 300. And let the specific heat for the milk be 2,000. Okay. Now, these numbers I'm just making up off the top of my head. If you were doing this in reality, of course, you'd look up on Google or in your textbook at a table of values, and you'd say, well, coffee is pretty much the same as water. So specific heat of water is 4186. Specific heat of aluminum, I'd look it up, whatever it is in a table. And for milk, I'd look it up and I'd have real values. But just to have values that are kind of clean, I'll use these. All right, so there we go. There's my problem. How do I go about solving a problem of this form? Well, the big key, if you can't do this, you can't solve the problem. So it all relies on, can you read the problem and figure out which pieces of information are important and which piece of information do you not need? So when I see this problem, I say, okay, well, what things are going to change? What things are going to have their temperatures change? I've got coffee, he's going to cool down. I'm in an aluminum cup. The fact that the cup's made of metal tells me he can change temperatures. If I said it's a styrofoam cup, a styrofoam is what's called an insulator. It doesn't like to change temperatures. And so usually professors or textbooks will use a styrofoam to mean you don't have to worry about this item. Okay, but an aluminum cup certainly can heat up or cool down. So aluminum's important. And then the milk. The milk is cold. When I put it in a hot coffee, it's going to warm up. So when I read this question, I say, aha, I'm going to have some Q for the coffee plus some Q for the aluminum cup plus some Q for the milk. And if I add up all those energies together, I better get 0. And so now all I have to do is replace these Q's with Cm delta T. So there's going to be Cm delta T for the coffee plus Cm delta T for the aluminum cup plus Cm delta T for the milk. And that's going to be how we solve this problem. At this point, all we have to do is plug all the data we have from our problem into this equation and solve for the unknown. What unknown do we have? We're looking for how much milk should we add to the system, which means we want to know the mass of the milk, that thing over there. Everything else we should have. Okay, well, let's try plugging numbers in. So we say, all right. Specific heat for coffee. Well, I'm given that in a problem. That's 4,000. Mass of the coffee. You have 1 kilogram of coffee, so 1 kilogram. Change in temperature of the coffee. That means, remember, delta T means final temperature minus initial temperature. Okay, so what will be the final temperature of my coffee? Well, the point of the question is the coffee starts at 90 and I want to force it to get to 70. So the final temperature better be 70. So 70 degrees Celsius is my final temperature minus the initial temperature. I'm told I start at 90. So 90. So there's everything for the coffee. Now I move on to the cup. Specific heat of aluminum given in a problem is 300. The mass of the cup, 150 grams. Grams is bad. I have to convert to kilograms. So it's 0.15 kilograms. And then the change in temperature of the cup. Now here's an interesting thing. You're not really told anything about the cup except for its mass. You're not told the initial temperature of the cup or the final temperature of the cup, but intuitively you know the values. Firstly, the point of this problem is that once you add everything together, they will all reach the same final temperature. That's what calorimetry is all about. The final temperature of all your objects is always the same. So if the coffee has to get to 70, then so does the cup, and so does the milk. So the final temperature of the cup is 70. What about the initial temperature of the cup? I'm not told what the initial temperature of the cup is. But again, intuitively speaking, if I told you, you just put a bunch of hot coffee into a metal cup, and you know the temperature of the coffee is 90, then you can assume the cup itself is also at 90 degrees. Right? We're not going to say, oh, I just put the coffee in, so the cup didn't have time to heat up yet. You just assume if the hot water or the hot coffee is in a metal cup, then whatever the temperature of the coffee is, the cup better be at that same temperature because it's holding it. Now, again, if this is styrofoam, which is an insulator, then obviously when you touch styrofoam, it's not hot. But if this is a metal cup, it will feel hot because the metal of the cup is the same as temperature as the coffee. So you assume whatever the temperature of the stuff in the cup is, that's the temperature of the cup as well. So initial temperature of the cup is also 90. Now the last piece, the milk. Specific heat of the milk given is 2,000. The mass of the milk, that's what I want to find, so I leave it as M. And then delta T for the milk. Again, the final temperature of everything is 70. So that's 70 minus the initial temperature. Well, the milk, I'm told specifically, is at 5 degrees. So you just pulled it out the fridge. So initial temperature of 5. And there we go. Cm delta T for coffee, Cm delta T for cup, Cm delta T for milk equal to 0. And now it's just a matter of the algebra solving for M. This looks like a big long equation, but it's actually fairly easy. Just take each term one at a time. And you say, okay, 70 minus 90, that's negative 20. So 4,000 times 1 is 4,000. 4,000 times negative 20 is negative 80,000. The next term. This one, maybe you can't do it in your head, so we do it on our calculator. We would say 300 times 0.15 times negative 20, and we get negative 900 for the second term. And in the third term, we're going to have m times some number. What number? Well, 70 minus 5 is 65. And we have 2,000 times 65. So 2,000 times 65 gives us 130,000. So those are the three things. Set it equal to 0. All right, we continue simplifying down. Minus 80,000 minus 900 is minus 80900 plus m times 130,000 is equal to 0. Bring the 80,900 to the other side. We have m times 130,000 equals 80900. Divide over the 130. And we get m is equal to 80900 divided by 130,000. 0.622 kilograms. So how much milk should you add? 0.622 kilograms of milk. And this is what you're going to do for all of these questions. Okay, no matter what it is, the system will be given to you. In this case, there's three pieces of our system. There's coffee, which is going to change temperature. There's the metal cup, which will change temperature. And there's the milk, which will change temperature. So Q for coffee, Q for aluminum, Q for milk. Replace those Qs with Cm delta T. Each one has its own Cm delta T. From there, plug the numbers in for all of these variables. You're going to be given every single piece of data. One of the pieces of data will be your unknown, the thing you're trying to solve for. For this particular example, we're looking for how much milk, so we're looking for the mass of the milk. One big concept to understand is if you're working with calorimetry, then you will always have the fact that the final temperature is the same for each object in your system. If you have 10 different objects, you let them sit a while, you mix them all up, eventually all 10 objects will have the same final temperature. Now, they may have different initial temperatures, but their final temperatures will always be the same. Another concept to know is if, when you're getting these types of questions, if you have a vessel, which is made of metal or a conductor, it can change temperature, and you have a fluid in that vessel, then you could usually just assume that the initial temperature of the fluid is the same as the initial temperature of the vessel. Or let's say you put a metal spoon to stir the coffee. Well, if the metal spoon is sitting there in the hot coffee, just assume the spoon starts at the same temperature as the coffee. So sometimes it may look like you may not have one piece of information, but you really do. It's just you have to use your intuition to remember it. Once you've written out all the data and you have your single unknown sitting there, then just little by little, use your calculator, simplify down all the numbers until you have a nice, neat equation like this right here, which is fairly basic algebra problem to solve for your unknown. So, any questions about this particular example?
I'm sorry, why was How's the aluminum 90 degrees?
I'm sorry, you were cutting out pretty bad there. Can you repeat that?
Why was the aluminum 90 degrees?
Right. So because in this case, I had the coffee was in the aluminum cup before you put the milk in it. So just to simplify things, we always assume that if you have hot coffee in a metal cup, it had sat there a while. So the temperature of the coffee being 90 heated the aluminum cup up to 90 degrees as well. So whenever you have something like this where there's a vessel, you put the liquid in the vessel, just assume the vessel and the liquid start at the same temperature. Of course, in reality, if you just poured your hot coffee into a metal container, the container hasn't yet heated up. But we're just going to assume, just like in first semester physics, there's no air resistance. Here you say, okay, let the cup start at the same temperature as the coffee. And it's only the milk which starts at a different temperature. So you could always assume that for all of our problems, unless it's stated otherwise. I could have given you a temperature in the problem, then you use the temperature that's in the problem. But if it's not given, then you could just assume, oh, I had hot liquid in a metal container. That container heated up to the same temperature as the liquid. Okay. All right, let's do another example. This one will be a little bit bigger of a pain in the butt for the algebra, which is why I want to do it with you. But it's the same process. Example 2. Let's say we have exactly the same setup. You have 1 kilogram of coffee at 90 degrees Celsius in a 150 gram aluminum cup. You add let's say 750 grams of milk at 5 degrees Celsius to the coffee. What will be the final equilibrium temperature? So, very similar question. Same things in our problem. The difference here is I tell you how much milk I'm going to add, but I don't tell you what the final temperature will be. You need to tell me the final temperature. Okay, so let's try it. You say, okay, first of all, what are the things in my system? There's going to be coffee, so there's going to be Q for coffee. There's the aluminum cup, so Q aluminum. And there's going to be the milk, Q milk. Those are the only 3 things in my system. Set it equal to 0. Again, each one of these Q's is Cm delta T. So Cm delta T for coffee, Cm delta T for the cup, and Cm delta T for the milk. Now we plug our numbers in. Okay, coffee. We're told from the previous problem, the specific heat for coffee is 4,000. The mass of the coffee, we start with 1 kilogram. And now we have the final temperature minus the initial temperature of the coffee. Well, the final temperature I don't know, so let me call it final temperature. But the initial temperature I do know, it's 90. So there's Cm delta T for the coffee. Now for the cup. Aluminum, specific heat, told it's 300. How much aluminum do we have? 150 grams, so that's 0.15 kilograms. Delta T, his final temperature. Well, again, I don't know the final temperature, but it's the same as the coffee. Everything's going to have the same final temperature, so I call it TF, just like the coffee. And his initial, again, because I put the hot coffee in the cup, I'm going to assume the cup starts at the same temperature as the coffee. So his initial is also 90. And then the milk, plus specific heat for the milk, let's call it 2000. I'm told how much milk. I add 750 grams, so that's 0.75 kilograms times final minus initial. Again, I don't know the final temperature of the milk, so I call it final temperature. But I do know his initial temperature happens to be 5. And now I set that equal to 0. And now this is the equation we have to solve. Notice there's only one unknown here, but it appears 3 different times. TF is in each one of these terms. So now I'm going to have a little bit more algebra to do. I'm going to collect all the TFs, all the other numbers I'm going to bring to the other side, and I'm going to solve for TF. So now the rest of this problem is purely algebra. All the physics is over with. So let's try it. How am I going to do this? Well, I have 4,000 times 1 times TF. So that's 4,000 times TF. And then I have 4,000 times 1 times negative 90. So I get my calculator. 4,000 times 90 tells me minus 360,000. Okay, so the coffee piece, this piece right here, gives me 2 terms. 4,000 times 1 times TF, that's the first term. And then 4,000 times 1 times negative 90, that's the second term. Done with that term. Now I move on to the cup. Same way, 300 times 0.15 times TF. 300 times 0.15 gives me 45 times TF. And then 300 times 0.15 times negative 90 is 4050. So that term is done. And now the last one, the milk term. I've got 2,000 times 0.75 times TF is 1,500 times TF. And then 2,000 times 0.75 times negative 5. 2,000 times 0.75 times negative 5 gives me negative 7,500. Equal to 0. Okay, so in this point, you have to be very careful and organized about simplifying this out. I'm just distributing through the numbers. Each one of these 3 big terms gives me 2 different terms. The thing multiplied by TF and the thing multiplied by whatever the other number is. Okay. Any questions about that step? Because that's the hardest step of all of this stuff. All right. So once we're at this point, the rest is fairly easy. Collect all the things with TF. So what do we have? We have 4,000 TF, 45 TF, and 1,500 TF. So add them all together. 4,000 plus 1,500 is 5,500, plus 45 is 5,545 times TF. And then the numbers, minus 360,000, minus 4,050, and minus 7,500. Well, let's see. 360,000 plus 4,050 plus 7,500. I get minus 371,550 equal to 0. All right, well, now you can see the rest is fairly obvious about the algebra. Bring the number to the other side, leaving TF on the left, and then divide over. So we'll have 5545 TF on the left equals 371,550 on the right. Get TF by itself, divide over the 5545, and you get TF is this number divided by 5545 gives me 67 degrees Celsius. Now, before I box this answer, I want to see, does it make sense? Because sometimes I could look at the answer and tell if it's wrong, or I could look at it and say, well, it doesn't seem wrong, so I can be confident. Let's look back at what the question said. Question said, you have some really hot coffee at 90 degrees. You're going to add some cold milk to it. What's the final temperature? Obviously, the final temperature better be something less than 90. You put something cold in something that was 90 degrees, it's going to be less than 90 degrees. What did I get? I got 67. That's less than 90. Seems okay to me. If I would have gotten 107, then I'd say, wait a minute, that doesn't make sense. I started at 90 degrees. I put something cold in it. How in the world did it get warmer? At that point, I'd look back and say, okay, I must have made a mistake in my math. Let me be careful and look at what I did. Here, I got something that at least intuitively makes sense, so I can be confident. It might be wrong. I still may have made a mistake, but I can't tell if I made a mistake, so I'll just accept it. So I definitely suggest on a test or homework, as you're working these problems, before you box your final answer and move on to the next one, see if you could tell if there's an issue. You'll never be able to tell if it's definitely right, but at least you could say if it's definitely wrong. In this case, it looks okay to me, so hopefully I did all the numbers correctly.
I have a question.
Yeah.
Okay, so the first one is that for final answers, we don't have to use like the decimal points.
Yeah, you
Random
should,
number?
but in this case, when I did on my calculator, I got 67.00 something. So that's basically 67. Usually what I do, and I differ from a lot of professors, just because what we're doing, you don't have to be so crazy about things, is the significant digits stuff. If you're in another class, you better follow significant digits because they'll want it. For me, I don't say, let's look at all the numbers in my problem and do the true rules of significant figures. I say usually keep 1 or 2 decimal points. So I would have, except in this case, it happens to be 67.00138 or something. So keeping 2 decimal places would have just been zeros anyway. But yeah, if when you're doing this, if it was 67.2, go ahead and put 67.2, because you're right. Sometimes the rounding can make things look wrong if you round too much.
All right,
Okay.
and I have and the second question is, you said that like I could to check, like if I were to check, it's a lot of work, but if I were to check, I could just plug my answer back into temperature final, right? In this case.
Yeah, you could go back to this point here, to these 3 big terms, and everywhere you see TF, put this 67 in, and see if you add up those 3 terms together, do you get 0 or about 0? Because again, the rounding, if you wanted to do a full-on check, that would work for sure. But I found, generally speaking, most issues, if you get something wrong, you could look at the answer and tell if it's super. Like if I got 3 degrees, I know that's wrong too. Even though it's less than 90, which it should be less than 90, it's also less than the milk originally was. There's no way I can take something hot, put a 5-degree thing into it, and have it less than 5. So I know the answer has to be somewhere between 5 and 90. And if I get a number like that, it's probably fine. The big things to look out for is the number bigger than 90 or less than 5? Then you know definitely there's something wrong. If you happen to have the extra time on a test and you want to go ahead and plug it into the original equation, you're more than welcome to do it. And that will show you if it's right or wrong as well, for sure. Any other questions about this particular example? Now you can see this first question wasn't so bad. Yes, it had a bunch of numbers in it, but the algebra wasn't too bad because there's only one, the one unknown only appears once. So you could add everything together and it's pretty easy. This one's a little bit more messy. You have to distribute and then collect like terms and all of that. It's not bad. It's not like it's differential equations and it's super calculus or something. It's just kind of a pain, and you have to be careful not to make little mistakes here and there. So as long as you take your time and go one step at a time and distribute through all the numbers, just keep track of all the terms and work little by little, you should be able to get the answer. So this is an important example to try to do yourself. In fact, one thing you could do is change the numbers a little bit. For instance, you could say, let's say I add 1 kilogram of milk instead of 750 grams, and then rework it. I don't know what the answer is going to be, but I do know this. It's probably going to be less than 67. Because if I only add 750 grams of cold milk, and that reduces it to 67, well, if I add more cold milk than that, it should be even colder than 67. So I would expect 60 degrees or 58 degrees or something. Okay, so try the problem yourself. Take out a blank sheet of paper. Don't look at what I did. See if you could work it down yourself. Because this is how a problem on the test will look. You're given a problem like this, given all the data, and it's up to you to feed the data into the equations and keep track of all the terms and organize it all and solve for whatever the unknown happens to be. Okay. All right, so I think I'll go ahead and leave it there. What we'll do next time is we'll probably do one more example and then move on to the second half of calorimetry, which is called latent heat. And I think I mentioned it last time at the end of the class, but latent heat is one extra term that we're going to have to stick into these equations that allow for things like if I put ice in my coffee, the ice could melt. So you'll have a Q for the coffee, Q for the cup. Then I have a Q for the ice, because the ice is going to cool it down as the ice heats up. But then there's going to be extra terms, because then there's going to be an extra Q to melt the ice. And then there's going to be a third term, I'll call it water, because now that the ice has melted, it's not ice anymore, it's now liquid water, and that liquid water can heat up as well. So adding in the fact that objects can change their state, that is, they can melt or freeze or boil, will add extra terms to our equation that we didn't have to worry about before. Now, that's all it does. The term is easy. To melt, it's just M times L, where M is the mass and L is what's called the latent heat. Just like specific heat, each material has its own number. Same is true for latent heat. Water, it has a particular number for how much heat you have to add to melt the ice to make it water. Or to freeze water into ice, you have to take away a certain amount. That's what this L would be. So it's just one extra term you plug into the equation, but everything else we think of the same way. Cm delta T for this guy, Cm delta T for this guy, M times L for this guy, Cm delta T for this guy. Set it equal to 0, plug all the numbers in, solve for your unknown. So that's what we're going to work on next time, is how do we incorporate this extra thing that allows for melting and boiling that we didn't have when we just have objects at different temperatures that you put together. Okay, but on Canvas, I've got last year's previous lectures posted on there. You can watch them if you want to move ahead. I believe there's 3 lectures, the theory, and then 2 lectures on example problems. And there's also the practice problem set for all of thermodynamics. Now, obviously, we're not doing all of thermodynamics yet. We're only on calorimetry. So only some of them can you actually do yet. But at least those that we've gone over, you go ahead and start practicing. Start working them out, get some practice in. That way, when I post the homework for this, you'll be prepared and you could work the homework problem fairly easily. Okay, so other than that, that's really all I have for you today. If you've got no questions, you're free to go. I will see you on Tuesday next week.
Thank you. Have a good weekend.
All right, you too. Thank you.
Have a good weekend, sir.
All righty, you too.
Hello, Dr. Rossman. Thank you for the lecture today.
Oh, no problem. My pleasure.
I also want to say thank you for the letter as well. Yeah, I appreciate it.
Yeah, no problem. Hopefully they choose you. That'd be nice.
Okay, bye-bye. Yeah,
All right.
I'm excited. Hopefully they do. No, I know I got your other email in regards to the REU program at Penn State. So I'm already starting on that application as well.
Okay, cool. Sounds good. Yeah, as many as you can apply for, you increase chances for sure.
Yeah. Thank you again.
All righty.